So you've seen a lot of stuff today, and you know that big data is all about fancy visualizations and huge amounts of data, as you see up there. Okay, that's 4 petabytes of data. I'm going to show you why. But what this really shows is the performance of a plasma accelerator in experiment and in simulation. And they don't match perfectly, but they match remarkably well. But why is this important? Let me show you by changing the x and y axis. You can translate the numbers that you saw down there and that might not be of interest to you to very interesting numbers, actually. It's the depth of a tumor inside the body on this X scale. And it's the dose that you can use to kill the tumor tissue on this y-axis. So how does this work? That's a picture of how this works. You need a particle beam, a beam of ions, and that's the positively charged nuclei of every atom in your body. And you make a very, very precise particle beam that exactly targets this tumor and nothing else. We don't want to hurt anything else than the tumor. This is a very well-established technique by now. This is used in medical hospitals, but I'm going to show you why it's not very known. Usually, if you do radiation therapy of tumors, you use X-rays. You use X-rays because the accelerators to actually create those X-rays are rather tiny. They can be put into every hospital. And this is important because you might have a lot of patients that actually need this radiation therapy. But you see there, in color-coded, that the radiation that kills the tumor was distributed very strongly, while with the ion beam it was very much focused. What you see here is what these ion beam centers today look like. This is the Heidelberg Radiation Therapy Center. It tells you that it's a huge facility. It's actually really, really huge, and they make very, 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 very nice therapy plans there that really help the patients. But this cannot fit into a hospital. This is a very unique installation, and it's really expensive. What if we could make this really, really small? What if we could put this into our basement, as was just said? So this is our dream, this is our vision. We're not there yet. We're researchers in trying to test this research to bring this research into application. And we're doing this with high-power lasers. Why high-power lasers? Standard accelerator technology is driven by the highest fields that can accelerate particles. But these fields at some point really destroy the accelerator itself because it really ionizes the matter. It takes away the electrons of the matter and just leaves the ions, and this really destroys the whole accelerator. Those high-power lasers have this year received the Nobel Prize. This is a Nobel Prize technique, so we use this Nobel Prize technique to do exactly what destroys the accelerators. We use these power accelerators, these high-power lasers, to rip matter apart and use the very strong fields inside matter to build our new accelerators. So how does this work? This is our small accelerator in Rossendorf. This is not in the basement. We can go on ground level. This is nice. But what it basically shows you in a very, very schematic way is a small aluminum foil and a high-power laser pointing on it. You don't actually see the laser because it's invisible to the human eye here. And what you see here is a live demonstration, basically, of how these accelerators work. You take this foil, and the laser shoots away part of the foil, and this part of the matter is used to irradiate the tumor. So this is a really, really small accelerator, as you see. Of course, the laser behind this is still a huge machine, and we need to make it much smaller. But this accelerator itself is basically just the foil and the high power laser impinging on it. So how does this work? In blue and red, you see the laser coming in, and below that, you see the foil in green. And what happens now is that the laser really pushes all the electrons inside the matter away from the nuclei and accelerates those electrons. And I want to make one special remark here. This is a visualization of what we do in our simulations, and it might just look like this is a bit greasy or something. This is all the particles that are inside this foil. There's a saying that there are more stars in the heavens than grains of sand on the earth, but there are more atoms in a grain of sand than there are stars in the universe. So this is a lot of particles. And we need to really understand how these particles move when the laser accelerates them. Because, as I said, the energy of the ion beam is one of the most crucial things because it finally determines where we hit the tumor. If we hit the tumor, if we hit it by 1 millimeter off, you don't want that. So we really have to take care and actually make precise, and this is very important, control of these accelerators. So we have to understand them on the atomic level. We really have to simulate, because our models can only be simulated, all those atoms and electrons inside this foil interacting with the laser. And this is an exascale application. This is 4 petabytes of data, 1 petabyte of data produced every hour on the largest scale machine. And the simulation is run by a single PhD student who has to make sense of these 4 petabytes of data. So how do you come up with such a code? When I started, I was a single postdoc. There was no code. And since it was an exascale problem, there was surely no computer in the world who could run it. So I teamed up with the best people that I could find, and actually the best people I really think in the world, and that was Heiko Burau. Heiko Burau was a 19-year-old Jugendforsch Prize winner who won a 6-week internship with us. And I selected him to have a 6-week internship with us because he did GPU computing, something that is now used all over the place for AI and everything. I hadn't heard of GPU computing. I didn't know of it at that time. I just thought, this is interesting. Let him come in, and I told him, write a code in those 6 weeks that actually describes this. He did. In 6 weeks, this student made the first version of our code, actually with live visualization on the GPU. And it was fast. It was wrong. It didn't do the right things. But in 6 weeks, he showed that in principle it can be done. And that was amazing. So we kept up with this approach. We got new students in. None of the people on this picture, except for this guy in the middle, had at that time of taking, the picture was taken, actually had an academic degree. They were all students in their usual studies. So there was Richard, who was actually looking into understanding how radiation tells us about those acceleration processes. There is Heiko in the back, you might recognize him. There's René, who is a programmer. He's a learned programmer. He has never been at a university ever. And there's Axel in front, second-year diploma student. And I'm going to tell you about Axel later. So this is my soapbox car team. 4 years later, we were running on the largest supercomputer in the world back then, the Titan supercomputer at Oak Ridge. And the reason for this was because I told the boss of the Oak Ridge National Supercomputer at the GPU Technology Conference that his computer is too small for us. I didn't know that I told him because he was in the audience when I gave my talk. And he later approached me and said, okay, prove me right, you have access to the supercomputer. We did. And actually, a year later, he actually asked me, and this was in 2013, to be part of the Gordon Bell Achievement Award. So this is basically the Nobel Prize in high-performance computing. And so we were in the finals. We were of the last 6 of a huge amount of applications there. And this is really a visible thing. So we went to Denver and everything. Heiko was the first student who actually was allowed to go there, because we usually don't allow students to go to an international conference. But NVIDIA gave us some money, so that was nice, thank you. But the main point was, with our soapbox team, we were finally in the Formula One. And that's a very nice thing. But this didn't stop there. Axel finally showed, and this is what I'm going to show you here again, that you can actually now make, with these huge amounts of calculation power, make predictions that are not perfect, but very close, and now that are just based on the knowledge that we have how the experiment was started. We didn't know how the experiment ended when we started our simulations. We didn't want to know. We said, don't tell us. We want to see how the predictive power of those simulations is. And for this, it came up pretty well, because this is actually an absolute agreement in the number of protons. And this means how much dose you apply to that tumor. And this is important if you want to kill the tumor. As a scientist, you have to see that this is not the right thing. You still have to have error bars. So that's what we need exascale for. We nearly need to put error bars in this. But Axel, so this is how it then looks like in the simulation. But Axel did much more. He convinced me that we need to put this out to the community, because when we started, we didn't have a code. We made this open source. Axel developed, in order to analyze those 4 petabytes of data, an open data format, an open metadata format actually, that is now used within the whole community. He developed tools, or he helped to develop tools to now put the GPU code with a single source on all those top 10 systems in the world, using very different hardware architectures. And he actually also helped to do these live visualizations that now help us to do real-time visualizations of petabytes of data, where we can just play around with them. So for me, the digital revolution today, there's so much stuff happening. But the most important thing to me is to understand that we should look at talent in places where we normally don't look. That we welcome people that we normally don't welcome in our peer groups. And I think this is the revolution we will be seeing, because talent is where we don't usually sometimes look. And I think that's the most important about the digital revolution that I think I want to share to you. Thanks.